Good afternoon, gentle readers. Today is September 9, 2024. From a desk with Ross Finlayson here in Seattle, Washington. This Monday afternoon, moment in motion. In the last episode, what was introduced was the notion of the punctuated motion, that motion is a continuous thing with regards to the infinite divisibility of time and the notion that the motion is continuous, that from any point A to B there are no particular jumps, that by whatever path does not go around something, it goes through as such a thing. Then that punctuated motion are these notions of the stops and turns, as with regards to what were introduced as slightly technical terms, the hop, skip, and a jump, the leaps and bounds, and the lurch, as with regards to off-weight and dead weight, the lurch, and then as with regards to snap, crackle, and pop, the jerk and jink, which are usual enough terms, and then there's jounce, which is usually sits in for one or the other of those, and then jank was introduced as a slang term just to fill out a trio of those. And then as with regards to the idea that these higher orders of the acceleration were either going to be more significant components or trailing and farther off components, that then with regards to the literature, it is so that you can already find punctuated motion is sort of defined in the library, and snap, crackle, and pop, and jerk and jounce, and these such terms as relate to these notions of the higher orders of acceleration. So I was looking around a bit, and another concept that came to mind when I was reading about it a little bit was a portmanteau, which is the way to put two words together and make one word, of the absement. So for displacement, it's the idea of change in distance terms. And before here, there's been some talk about how length and distance, so they're the same units, have different terms, because distance kind of like length and time per time. Kind of like, not exactly the same as that speed and velocity are two different things. That velocity is a vector indicating both a magnitude and a direction, whereas speed is just the magnitude itself, or a scalar quantity. So absement is the idea that besides something like displacement, this is absent displacement. And so it's not the same thing as these higher orders and the infinitely many higher orders of acceleration. It's more of a zeroth order thing. And then as with regards to the 0 meters per second equals infinity seconds per meter, it kind of intends to entail a little bit of what is with regards to the singularity there at the same time. So today you can find that in somewhat modern terms, and introduced within the past couple decades or so, is this term absement. Now, one thing that I noticed about that, there's also a term associated with this acceleration called momentement. And so momentum, as is described here, is not necessarily the same, usually considered conserved quantity, that is more of pseudo-momentum, is conserved in the open, as it were. This is framed variously with regards to Nessie's hump and the pseudo-momentum. And one thing I was reading about this is as with regards to modern models of torsional dynamics in the tokamak fusion reactor was the setting. And so there's something along the lines of at least two kinds of angular momentum, and as well with linear momentum. And so that helps, and otherwise with regards to the four vector, and what otherwise gets introduced as usual enough terms in the quantum mechanics, which is the kind of the setting of this field, formalism, that there are already, of course, many different models of mechanics that have, of course, exactly these same considerations as with regards to the dimensional analysis, and with regards to how to pull together these fictitious forces as they're so upheld, when it ends up being that as things go from one system to another, these are the ones that become, in effect, the real forces. And so it just goes to show that with the notions of infinitely many higher orders of acceleration, that it's a concept that is indispensable in otherwise, the physical models, and as what we're just lacking mathematical models for it. And then otherwise some of these notions as with regards to the classical mechanics and the absement, it was this portmanteau it tends to entail, which is kind of in the unit of length time instead of length per time, as with regards to being the antiderivative of displacement in its formal description. Then gets into these things like the stop derivative and some of these other ideas of what goes on in terms of that vis-a-vis when it goes from one or the other of terms being of or per, by or per, the units of these things, that it's a thing. And it's all one thing somehow. So this encouraged me quite a bit. And it encouraged me both for that I wasn't just entirely unawares of any of these things in the world, and it encouraged me a bit is that of course other people who are interested and curious in these same sorts of systems are trying to figure out these same sorts of formalisms, and otherwise it just encouraged me because it's not already such a developed field that I don't feel like I can actually kind of just figure it out kind of on these terms and end up with something that's kind of novel for its own sake. Another item that I thought was of quite striking interest was this. In some of the previous talks and kind of after the notions of the momentum and the potential and the force, since the description of the Mertonian school and Bradwardine and on De Continuo and the calculator in the Mertonian school of Oxford, which predates Galileo by 100 years, which predates Newton by 100 years, from which all this stuff comes, the notions of power over resistance or power minus resistance and these kinds of things. And as so far as then we have seen arrived at today, the notion of inertia, which is kind of a linear quantity, and it's kind of what's there. And then momentum is just kind of like, well, it's kind of just like the derivative of that. And so it fits into force equals mass times acceleration. And there's, with regards to that being, shown and established, that's the relation to massy quantities, is this. There was a discussion about space contraction, that how even in the classical, whether it says of the striking of a golf ball or the spiral of a football, or otherwise the spiraling effect as of perhaps a javelin or the rifling of a bullet, that there's an effect called the Magnus effect. And this is studied largely in terms of the baseball and the idea that with a particular amount of spin on the ball or the peloton, the projectile, pelote in this sense, not quite so much the keep, as it were, that the Magnus effect is that there's a measured lift of this item as with regards to its travel. And then so the idea is that it's not an aerofoil in effect, and so instead it's the idea that it's the space contraction affords it this momentum increase and it actually makes for sort of heft instead of lift, and so that its gravity doesn't give it as much drag. And so a way to read that is that it's a real classical effect of what's otherwise a fictitious force that is framing otherwise this balance and symmetry of forces, in the case of a projectile lift and drag, of instead this Magnus effect as kind of the superclassical Magnus effect. So I thought that was kind of interesting to relay because it helps to provide what is otherwise no necessary reason to attach it to any kind of chance or hope that it would have a simple physical experiment to so display such these aspects of the pseudo momentum, this Magnus effect, this Nessie's hump, and these such things. So the rest exchange momentum is with regards to the space contraction in the classical, right? And so it doesn't really say much about anything being wrong at all with Newton's laws or Galileo's laws or these Mertonian laws, but it does help reflect on the entire discourse and like the viva vis-a-vis the V matrix, these what the thinkers of the day very much put their minds to, and as what with regards to what we have is like, this is our linear curriculum and this is all there is about it, and as we're nominalist fictionalists, this is all we're going to say. We won't listen to anything but that. Has that then to bridge these gaps, to bridge these, make these analytical bridges, or the Analytische of what are these inductive impasses, is as what's kind of necessary to make for a fuller model, because 0 meters per second is infinity seconds per meter. So that amused me. There was an article the other day, and it was just like heresy in physics, it called itself. And I thought to myself, well, that's just rather strong words. I'll browse this article and get an idea of what they're about. And this was the one where it's like, well, if you throw something high enough off the Earth, it doesn't make a parabola anymore. It enters an orbit. I'm like, that's old news. That's old wrapped as new. That's not even counter to what we're told at all. That you must have been living in a flat Earth for you to think that is news. But what I was wondering if they would get into something more along the lines of it is that you throw a spinning ball, it's not quite parabolic, because it's actually more linear on its descent. And then as it loses energy, and then because it's dispersing this to kind of hold itself aloft, to maintain its heft in flight, as it were, vis-a-vis what's called lift, as it's perceived to be, as it's measured to be, as it's modeled to be, as it's given its effect to be, that I thought that would be a pretty particular thing. Kind of like I saw an article the other day, and it's like, QM and GR are unified. I'm like, oh really? That's great. They must have a fall gravity. They must have unified the strong nuclear force with gravity. They must have made a space contraction. They must have put SR behind GR and set up the SR as local. And it was more along the lines of like, we log normaled our G2 muon, and now our bias is off the slant. And it's like, well, I see you slanted your bias a bit, but it really doesn't speak to having a unified general relativity and quantum mechanics at all. And there wasn't gravity really so much put in the picture in this one either. So it's hard to find something that really kind of offers something that seems like the physics. So after the Faraday rotation, I had been looking at this fact book from 1846. And it introduces things like with Faraday's original experiments where he does this magnetization of light. I'm like, come on now. I have already established here that from what I understand, that there's like no electromagnetic character of light at all, except for this equivalence of the energy, the photon and the electron in the electron physics and the optoelectronic effect. That's it. And it was like, well, Faraday actually, he takes some kind of polarized light and it goes through this boron silicate, and he then magnetizes that, and it comes and goes, it blinks on and off as with regards to whether it's magnetized. So he's magnetized the light in this medium at least. And so then, some 20 or 30 years after that, or for the 1903 Nobel Prize, Zeeman won a Nobel Prize for kind of putting that down. He's like, hey, after the great success of spectroscopy, we got Lord Rayleigh and Lord Kelvin over here, and they're advised us that, you got Clausius, and so you got statistical ensemble coming up, so we put on a sodium lamp instead, so they changed the experiment, it's different. And he's like, and so we got this 2 lines of sodium lines, and we'll just pick one, and it doesn't show up. So it's not falsified that his original experiment was a thing, but at the same time it's like, but it lets a bunch of these other cards neatly fall into a stack of a house of cards, and so we'll just let it stay so, and hand it a Nobel Prize and carry on with this great, magnificent, successful work that includes special relativity and quantum mechanics, and makes possible the digital circuit of today, where it's like the most simplified thing as it can be to make digital circuits, special relativity and quantum electrodynamics. So I thought that was of some relevance, because then this whole tokamak bit mentioned earlier was all about Faraday rotation in 21st century and this kind of thing. And then another thing that was in this fact book from 1846 was about phosphorescence. And I don't really particularly understand the notion of phosphorescence so well. Once had a night light that operated on this principle before they had light emitting diodes and everything. And you're familiar with light emitting diodes or LEDs, and the technology is all sorts of things as small of light bulbs, lamps, television displays, and all such matters of technology. The light emitting diode is a very well understood active electronic device that is mass manufactured and very well understood. So phosphorescence is a different thing. And the idea of how it's built is it's a particular gimmicks, gigas, what would we call these? It's not so much for the effect is less understood. And so what it described was this sort of second spectrum of the light in the phosphorescence. And so this struck me as kind of profound, and it relates here to kind of these things about like the hop, skip, and the jump. Or when we study something like the solar system, it's like, well, first there's a concentration that's close, and then there's a gap. And then there's some more, and then there's a gap, and then there's some more, and then there's a gap. You can also relate it to the electron orbitals, which of course are the most successful, highest precision, measured, scientific, stoichiometric thing at all, what governs atomic chemistry altogether. That there are these outer rounds and these outer bounds. And for example, is when they're studied the transuranic elements of so when you look at the periodic table of elements, and it starts going out with just the electron orbitals of the outside ionization potentials, the ions mostly, and then it gets into the actinides and lanthanides, and all this stuff splits out and grows underneath that in the second thing. And these become the volatile elements, where the half-lives are very much lower than the lower elements, and if their usual isotopes as they're usually encountered. And many of these are not even found to exist except as via transmutation in the laboratory by the combined fusion and fission is via nuclear transmutation of elements to make the higher, heavier elements. So what's posited in that theory is what's called an island of stability. And so there's not so much of the beyond the theory yet for it, but there's a theory for it that explains in terms of these potentials and in terms of this structurally that at some point in time they will be able to possibly develop a heavy enough element that will have a long half-life again. Compared to today, it's like iron is the center of the table of elements and these kinds of things. That it just helps to reflect on that, this spectroscopy and the sodium lines. And for example, there are at least 3 sodium lines. So when Zeeman won his Nobel Prize, it was like, did you know there was a third sodium line? And he would have to say, it was like, no, I did not. And so on is with regards to what's otherwise the idea of spectroscopy is that accordingly each atomic species makes exactly one line, a discrete line of otherwise this infinitely varying range of the things that they start to branch out and bracket out and to make a bigger and fuller picture of this in the combinatorial expansion, the combinatorial explosion of these things. The discrete and the continuous and discrete. So that just goes to help inform that there is still a lot of things in physics that are empirical and not so much explained by the theoretical. And every one of these is pretty much called an effect. So the effect is pretty much anything that is its own empirical milieu or domain. And so, like, Siemens got an effect. How about the breakdown of Schottky diodes? Well, is that an effect? Yes, it kind of is. Or how about things like the skin and core effects of fluids? Well, that's just because electricity has one and liquids have the other. They're entirely opposite in that way, but alike in every other way. Is that an effect? It's like, well, yeah, one in terms of the other it is. Or the notion of that there's various effects in devices. For example, various junctions like the Seebeck and Peltier junctions and such, what can make light from heat, heat from light, and vice versa, and also as with regards to electricity and heat and light. Then that these days they consider the designs of the electrical circuits not only the plainly governed by Leonard Wietrich potentials and the activity of the positive, negative, positive, or PNP transistor and a gate array of NAND gates that comprise a digital logic circuit and what's called standard logic. The custom logic is anything that could be the system on a chip. Everything involves the effects of phosphorescence and photonics to the optical and this kind of thing. So I was just kind of encouraged and reminded that there is a whole galaxy of events. There is a whole zoo of what they call the exotic particles, these being the muons and all a bunch of other different kinds of things, whatever all was discovered in the particle mechanics, the accelerator physics of the 50s, 60s, and 70s, when these were earlier just very widespread and of very many sorts, instead of all just like pointing at the red dot. And we know that NIST data releases new fundamental constants every 5 years, and they're not just more precise, yet they're smaller according to the energy of experiment. So in the energy and configuration of experiment, there's a lot of room for these effects. They're still all real, that are just lesser explored. And it goes a lot to show that we all put a very great value on the standard linear curriculum and the fundamental and the premier theories of the day, and at the same time, in many halls of academia, in the physics department to the philosophy ward, there are these ones that come up with these ideas that it's like there is another crisis in physics. Because when physics came to the crisis of the ultraviolet catastrophe, what is waves, what is particles? Finally, they hammered it down and said, well, it's particles, and we got electron physics, and Millikan has measured exactly one, and then we're also able to ascribe to it exactly to the atomic numbers and the species of the atomic elements. That is why it is so. And then we have theory that backs this up with regards to the interchange of these equivalencies of energy in those various forms of the quantities. And that is what sits underneath is those being so fundamental that those are elementary in the theory. Now, as we've considered here, those are just kind of reconstructive in the theory from these other primary theories, other quantities as they sit. And that each one of these conservation laws about energy can also be exactly formally and in much the same way, without any loss of generality at all, in a very strict sense of the mathematical words, and without any loss in expressive detail, and with capturing the full intent, still the meaning of what is the law of the theory. The continuity law is also this conservation law, and vice versa. And so then when they have the running constants, like NIST data proves every few years our thing, and then we have the quasi-invariance for the supersymmetry and the high energy and the low energy, and then the plainly anti in the mesoscale in the supersymmetric sense of the virtual, which is very, very familiar to all students of quantum mechanics, as after Dirac's positronic C, and as with regards to what has become quantum electrodynamics and the scattering and tunneling effects, modeling waves as particles, that the ultraviolet catastrophe was resolved by Lord Rayleigh and Kelvin as we were given these names as they're Britishers, and they got great rewards for their scientific achievements and developments, and the promulgations of this throughout the society. And Clausius and the schools that arrived at the statistical ensemble, which gave a formalism for the adiabatic to add up all this stuff that went one way. After the caloric was put away and the chaleur was the model of heat. After the ether was put away and relativity was put forward as of solving these interactions in the gauge. Then that later, much later, in the 50s, 60s, 70s, arrived gauge theory, for example, arrived muon physics, but this was where the at the same time and contemporaneously as quantum mechanics became a thing, de Broglie made sure, it's like, I am still looking at waves here, is so that particles and waves are the same milieu and somehow contradictory and juxtaposed, yet also holistic. So the ultraviolet catastrophe making electron physics and a particle physics still has particle wave duality, and that is one of the most central and important superclassical concepts that there can be, so that we're not absent and bereft of an entire world of the theory. And so for what it is, it's good, in many respects perfect, the atomic chemistry, and that which affords for other things being held constant and not of particular energies or configuration as to be relevant, exactly what goes into, say, a combustion engine with a fuel air mix and a particular heat, and as with regards to the Carnot cycle, or Sadie Carnot, Clausius and Kelvin, the second law of thermodynamics, which defines then thusly all the reasons why and how the energy is equivalent under these same conditions mathematically. So we have the adiabatic, and what about the non-adiabatic? We have the particle, and what about the wave? We have this and then that, how to bring back together these kinds of things and how they are. Well, that's kind of the role of physics today, and why there's again a sort of infrared catastrophe to complement the ultraviolet catastrophe, and a muon neutrino physics to complement the electron physics, or if you will, a neutrino muon large hadron physics to complement the electron physics. I just made that last bit up together, but it's got to add up. Kind of like when you look at the ultraviolet and radiation, is like, well, what happens when something goes infrared and there's nothing left of it as light, but there's still energy? Well, that's heat, and so it's just kind of one heat. Well, what happens when it goes to the ultraviolet is like, well, it kind of breaks out three ways. There's purple, indigo, and violet. So we call that one way, and as if the electron physics comes down, because light has then got two spectrums at least. Optical light is special, see. Optical light is this free model of flux of information, if metered, for each of the, otherwise these regimes go in the various ways. So coming up around to that, it can help a lot to have it helps a lot to have, first of all the schooling of these things, which would otherwise just not exist. Particle wave duality, particularly. After a theory that includes calculus and infinitesimal analysis and the convergence of infinite series and their perfect values. And then as well with the conceit that there are limits, and then many times we don't have analytical and closed forms for things, even in the mathematical models, besides the physical models. Then for the classical, of course, it's like, this is our tape and this is our stopwatch. Have fun, get to it, that's it. Here's also the classical description, that's the end. Everything else you kind of have to tape, as in masking or painting tape, to stitch together these pieces piecewise, as otherwise, by the time it makes a 90-degree turn, everything is off. Zero is what's left. It's asymptotic. So these are the things that help then make it so that when we look for a way to figure out the equivalency principle, is gravity and acceleration the same? It's like, yeah, as long as we're just sitting here talking about it. Yeah, is it so that it really makes it so that there's not lens throwing experiment and frame dragging? It's like, well, you know, they did send an experiment up into space and it got far enough away from Earth that it kind of measured where it would be pulling, and it's kind of the same as Earth. And then the one they flew up next to the sun kind of gets that kind of distance as well. So it's kind of like in our gravity well, we kind of got the inside and the outside of it, this so-called otherwise gravitational equivalence. Oh, really? When did you hear about that? It's like, when did I hear about that? They haven't even announced it yet. No, I'm just joking. They have announced that's kind of like lens throwing in the Parker around the sun. So once you learn about these things, then it's kind of like, so I hear over in France after J.S. Bell, they got the aspect-like experiments, and so I figured to try and gain some inspiration from the Spaniat today and see where we're at in reading from philosophy and physics. Let's take a look here. And so we've been reading this book here called Bernard de Spagnat's on Philosophy and Physics. Several months. And so it's not each day that I open this book, but it's among other things I'm reading, it's something to do. And so on page 160, last time it was noted on page 88, and now here is page 160, section 7.2.2. of criticisms of operationalism. So operationalism is basically that when we talk about particle physics, it's not like there's a guy who has the reflexes of a bat or whatever and can pick with a pair of tweezers an atom and say, aha, I've got one. All right, all we can figure out is like we've devised a detector. And so what does this detector mean on the atomic scale? It's like, well, as operationalists, we've figured out that we've got the detector. And so then we just can only say whatever else is in the theory. We're model physicists, and hey, we can measure maybe sometimes just a flow. Like after you get 10 million, it would add up to one, or this and that these kinds of things. And so when Despondent gets into operationalism, part of it is as regards like, are we just confirming our biases or our presuppositions, as if we were to have made this model of the statistical mechanics and the Born rule and the Pauli principle. And so it ends up being that our model of particle mechanics, which is kind of a conceit and a concession to that they don't really exist, because it's just the scale of the things somehow continuously does or doesn't make a thing. Well, that's operationalism. These are the pocket watches that our accelerators smash into the walls, thus that we can scrutinize their contents and figure out what's in them. So I'll just read a few words from this and see what he has to say. Above, analyzing various ideas progressively made us impart some genuine cognitive weight to statements and laws whose nature is but predictive. And of course, as soon as we take quantum theory specifically into account, the quite basic role this theory attributes to the observational prediction rules still reinforces this standpoint. Consequently, we must take an interest in the philosophical approach called operationalism, and the class of theories labeled instrumentalist. In short, operationalism or instrumentalism, we shall not try to distinguish between the two, is the view according to which the hard core of a theory, here we think particularly of theories of mathematical physics, is its ability to be used as an instrument for predicting observations. Because we don't really have otherwise available to our senses what would be these things. Operationalism was severely criticized by thinkers of various schools. Before analyzing these criticisms, in order that the meaning of the comments to be made of them be adequately understood, let us first remember that we noted above when discussing open realism, section 5.1.3, concerning the notion of explanation. Here we might ponder Nozick's explanatory factors and what suffice.
We noted there that even though the great physical laws do depend very much on us, still the idea that this dependence is exclusive meets with serious difficulties, so we can hardly avoid considering that they also depend on something else. So this is the idea that this can be very far removed from the idea that there's like the quantum observer effect is at all related to what in the popular culture has made it as like, as like don't watch the toaster. The toast will never pop up as long as you're watching the toaster. This is a usual allusion made to something like the quantum teapot never boils, or something like that, as with regards to what are otherwise these effects that flow when they're unrestricted, that any kind of instrumentalism or instrumenting this detector somehow, where to instrument a situation is to place a detector or sensor into a situation, has that its mere presence at all changed the configuration space of what otherwise is this ongoing experiment free of this other attachment that's been so burdened upon it, as it were, vis-a-vis trying to explain within whether the theory it's because there are superclassical effects and it just spoils the wave, and as to regards whether it's like, well, it's metered in itself, so what comes out is digital. These are various things that get into it. Now, I didn't mean so much to get quite into the quantum theory in this talk, but there's a lot going on by the time it got going with regards to the electron physics and this neutrino muon hadron physics, or the supersymmetry of the day, with regards to the crisis in physics that general relativity and quantum mechanics are together, our premier theory, but they're two different theories, and they're 120 degree orders of decimal magnitude apart and facing away from each other. Gravity, of course, is in the middle, doing nothing by theory and all our principles of philosophy at all. All one theory. That is with regards to, otherwise, all we were talking about the last few talks are classical mechanics and the superclassical implementation of same by this sum of history is sum of potentials, which again, it works up to be the same theory as these quantum theories and cosmological scale theories, all one theory. Back to disappointment. We noted then that even though the great physical laws do depend very much on us, still the idea that this dependence is exclusive meets with serious difficulties, so that we can hardly avoid considering that they also depend on something else. See, here there's basically the opposite notion. It's like, it is an objective realism. We're lucky we have a glimpse of it at all, and whatever it is it. We're not privileged. There's no privileged frame. Yet each is its own. They're all privileged frames. This argument calls, of course, for more extensive analyses to be undertaken in the second part of this work. But as we should, its validity depends in no way on conjectures concerning the accessibility of the something else in question. View of the following discussion, the conjecture of interest, which is logically tenable, though unusual, we come back to this point later, is that this something else, while not being scientifically knowable, still has structures that indirectly have some effects on our laws. So that such an elusive, independent, or ultimate reality may be thought of as explaining the existence of the said laws. Now, of course, when within the framework of an operationalist theory, we are led to make use of the word reality, it is not that reality we refer to. It can only be the notion introduced in section 4.2.3 of an empirical reality composed of the totality of repeatable and communicable human experience. So let us firmly keep in mind the fact that the word reality is not univocal, and that it refers or may refer to either one of these two concepts. The distinction is crucial. So as a philosopher, after Duns Scotus, there's introduced the concept of univocity. Univocal is when there's a univocity. That one voice, as it were, is kind of like that we all hear. And so our physics and modern scientism and logical positivism may arrive at that there is no such inner objective thing, because it would be unfair to somebody eventually, or to ascribe to something that's more than human, which is all that in this context of the thinking things that there are that can possibly perceive this theory at all would be. So this univocity that Desponier refers to is, in the one sense of physics, it's something that physics attains to and never gets, whereas it's something else that in our human thinking, when the philosophy includes it as primary, that there is a theory of truth or what at all. It's what we attain to, and it doesn't matter what we get. So they can be seen as compatible, univocity and haeccity, quiddity and quality, as we read from the medieval philosophers like Grosseteste on his theory of light, and Peter and Albert the Great of the, like, from 1000 to 1200 AD, that those were our premier theories of the day. After the 1,000 years before, with like Lucretius and films and images of light and a theory of free and fixed information. So simply part of our canon and all connected. The distinction is crucial. That much being said, let us examine the main objections to operationalism that have been made. One of them concerns the very notion of explanation. Mario Bunge, for example, in 1990, noted that, according to operationalism, hypotheses and theories are nothing but concentrates of experiences, consequently no genuinely explanatory role as imparted to them. But he pointed out the main role that theory is precisely to explain, which he claimed theory is only to the extent that they yield at least a rough sketch of what reality really is. He says, the point is worth considering when discussing the no miracle argument. We ourselves noted in the same vein that short from granting that miracles occur all the time, we have no other way of thinking and responsible than to consider that something exists. So it's super scientific. The miracle is at best super scientific. But then as in this with regards to the existence of the sum of histories, sum of potentials, the example was given as the rogue wave, which is out of the entire sea, out of nothing arises a great wave. That it could be a miracle or just an echo of a seashell as a metaphor. I am reticent or hesitant to ascribe just plainly a theological aspect to this or deistic aspect to this. Because while a monotheist monism may be super scientific, and insofar as a theory goes, it perfectly well explains many sorts of miracles as after belief, that many of those could also be ascribed to other aspects of super scientific belief that are connected to this same origin of things. All the omni is ascribed to be one thing. So it's perfection and omni and all what is what was attached with also its baggage of authority before the scientism, logical positivism and such eschewed entirely anything that could possibly remotely remind one of super scientific. That so this is reality is so. So insofar as that goes, this reality and theory of truth, that's this realist position and objective position, is kind of the same thing vis-a-vis that this anti-realist and this instrumentalist operational approaches are very much empirical, and thusly they do not need any other belief, desire, or motivation to make convincing the argument this way. They cannot. Our model physicist is given the burden and the strength of having nothing else than the theory written down, formalized, mathematical at all. So then largely we get into that mathematics owes physics these things. Insofar as it's scientific at all, It's mathematical because mathematics has a ubiquitous success in mathematical physics. Insofar as the explanations are beyond all of our comprehension, super us, it's super scientific. And so there's always still yet a plain and simple placement for that as a belief system, according to philosophy, of plain monism. And then dualist monism is just like weighing these kinds of things. However, at these places, it is extremely risky, if not strictly impossible, to identify the something with any scientifically and experimentally accessible reality. Then largely it's not necessary. It's just kind of like que sera, sera. What will be, but the future is not yet written necessarily. Vis-a-vis that for the predictive power of operationalist and instrumentalist theories is that one can make of these as after a reading of all the theory of science gives to some alien cult. It works just as well for them as it does for anybody else. It's objective. The weak point of Bunge's criticism analyzed here entirely consists in that, according to him, such an identifying is requested. Well, we needn't have that. We can just say it's a theory of truth, and it just like Nozick, it stresses that it's the fundamental question of metaphysics. Why is there something rather than nothing? And in a brief conversation I was having today, it was like the great work on philosophy that most people started with in the most printed book of all time starts with like there was nothing, and then there was something. In the middle it says there was nothing, and then there was a word. And so it just starts explaining and establishing that there's geometry, it's given. It arises for itself. There's a word, it's algebra, it's given, it arises for itself. Along with the operationalists, we shall consider theories to merely be syntheses of experience. We shall assert that they primarily predict communicable observations. We shall add that within vast but limited fields, they may nevertheless be formulated as if they bore on things, that is, in terms of an objectivist language that syntactically is descriptive. And finally, we shall, to repeat, decide to call empirical reality what such a description refers to. We shall unreservedly grant that conceived of in such a manner, empirical reality is much too anthropocentric to be of any use with respect to our desire of explaining physical laws. Not necessarily, because the more closely you can attach them with mathematical laws, like this space-time as a reticulated continuum, then that's the law. And these continuity laws and conservation laws, those are the laws. Least action is the law. What goes up must come down is the law. So these physical laws, this is part of, as it was put in its beginning, to be more and more appreciated, Despagnat's hedge, that he's balancing these careful extremes of science with respect to making more of this fuller synthesis of the thing. Admittedly, realists will object that such an explanation is purely ad hoc, from what he said, and we shall not at all on this supposed ground, demand that explains our physical laws, that we should deny any explanation is needed, but because we found out the explanation in question can only lie in the something mentioned above. And in this footnote, he says, in other words, Bunge's objection is pertinent only concerning an operationalist or operationalism or an instrumentalism raised to the level of an a priori philosophical standpoint bearing on the theory of knowledge. Purely methodological operationalism, such as the one here upheld, is immune to it. Which is fair. It's incomplete in a sense. And that reflects very well on a usual theory of mathematics that restricts itself to a single form of regularity, when in the continuum mechanics there might be like, well, there's three models of continua, but you can model them each other in terms of just one if you build out and axiomatize like an infinite limit, which you'll never reach, of course, and you'll be glad to agree that that's so. But then you'll be immune to not only it and its consequences otherwise of that tower of cards falling back down, but the rain getting in and this kind of stuff. Moreover, it must be noted that another objection expressed by the same author consists in just an act of faith in favor of the realism of the accidents. The accidents being just the order of things. Of course, Bunge granted that in physics, validation of ideas rests on experiments. He claimed, however, locit, that experiments do not constitute the object of the science. Well, our body of knowledge is sort of the object of the science. On the next paragraph, Despaniat begins, let us, for example, consider the two ideas at the same time, that a particle and that a wave function, alias state vector. If we consider wave functions not to be real, this, according to Bunge, implies that the very notions of wave function is void of any value. Well, yeah, I suppose. However, in quantum physics, it is quite impossible to do without this notion or equivalent ones, so that if we decide to follow Bunge, we must consider wave functions to be real. Similarly, in the same science, it is impossible to do without the particle notion, so that still following Bunge, we must consider particles to be real. In other words, if we take Bunge's assertion literally, we must consider that both wave functions and particles are real, either simultaneously or alternatively. Or try to figure out how they're unified in terms of the wave mechanics as a sort of that the particles are just the coalescings, the crossings of these waves. That ultimately they're just kind of the crest and trough, and that the other ideas that go into making for why it's a particle wave duality and not just one or the other, being electron physics, the ultraviolet catastrophe, and electron physics. That particle physics is as of a conceit, a concession to that we got to stop somewhere in atomism and democracy and atomism for atomic chemistry, for which is great. Besides that, it appears to just get smaller. Avogadro's number gets bigger, and eventually it runs out. These are called the running constants. So it's a thing that everything's just fantastic, and you have two fantastic theories 120 decimal orders of magnitude apart from each other coming together. Aristotle, McKeon's Aristotle. Let's take a look here what time it is. So, Griggs Hegel, or Harris's Hegel, I guess. If you recall, he was so quite proud of the airy heights of Hegel's thought. But insofar as it kind of gave the baton of this extended relay race to the logical positivists, it also gave them nihilism and its crooked cousin existentialism. When I say crooked, I don't mean necessarily in the criminal sense, as in the in the crooked sense. That if you recall some of our earlier discussions about the cyclic metaphysic, that Hegel is a torchbearer of the metaphysic. And so when he handed on this baton to say, and here, take logicism and positivism, he's like, this isn't Pandora's box where hope is left inside the box after all the evils in the world get out. You got to take this torch of metaphysics with you, because if you don't, that baton is going to spontaneously combust, which it does, which is great. And this gives us our infrared catastrophe, which makes for a new neutrino and muon and hadron, large hadron physics, all according to all the greatest and most high energy and high configuration experiments of the day, and having to add up all these experiments since the 1840s in Faraday through all these side deals, the particle zoo, and also just all the classical mechanics, which is still a largely an empirical theory. So Aristotle and Hegel are kind of held up as the idealism, the philosophy. So yeah, this is a good one. Cosmology in 2+1 dimensions, cyclic models and deformations of M21. Because what this gets into is making for the Zollfrei, and so that means it's like there are no closed time-like curves in our theory, and that just means there's no time travel, time reversibility has never been falsified, and all this kind of stuff. He's like, well, then it's really hard to have anything but the adiabatic everywhere. So he does this, he says, how about instead we make it so that every forward increment of time is a zigzag in time, is a tiny forward and back increment in time, is this vague fugue. It makes for Born's other rule, the restless universe, that Max Born was a physicist in quantum mechanics who came up with the Born rule, and that established for quantum mechanics that basically it's going one way or another according to these quantum probability amplitudes. Forget that it's continuous. You'll just have to make do with that. It's always at somehow at a right angle, and when that gets too small to tell whether there's right angles or straight lines, then forget about it, and you just have to start over. That's basically kind of how it works out. And then this scattering and tunneling is like these zigzags, as it were, back and forth, trying to add it up. This is just in the sense that actually that vanishes, becomes like a zero, a restless zero. So this is kind of the concept of what's the Zollfrei, if this is the same work here. Cyclic model, futures. We'll call a Lorentz metric, all of whose null geodesics are periodic, a Zollfrei metric. Notice that the property of being Zollfrei is conformally invariant. And so he says for this vague fugue, the vague fugue is a notion of the real numbers that everybody knows that real numbers are strictly in order until you get to the infinitely small. And then this kind of like this leaps and bounds stuff means they still go, they're rough though on the grain, and insofar as eventually some model of them is just like so. That they're both, it's like a particle wave duality for numbers of a sort. Applications of spatial data structures. This is the quad tree and the oct tree from about 1985, 1988. And the data structure that is the quad tree or the oct tree for the computer science and its applications. Source book on the space sciences. The Advanced Orbiting Solar Observatory. He gives the Planck equation, on the basis of his quantum theory of the emission of radiation Max Planck. You derive the equation. I sub P is the amount of energy, IV dV is the amount of energy radiated, so that IV equals 2 pi over H is constant over C squared, dot or times V cubed over E to the HV over KT minus 1. And so that E to the HV over KT is particularly relevant a bit here in terms of that not being zero. So that those terms together have to not equal to 0. But Planck times V is like when V equals 0, that equals 0. So then the denominator of this form would also equal 0. So that this is one of these singularities. It's just like you're talking about the operationalists and instrumentalists. I noticed that the default the vacuous case is prohibito. And so here then the idea is to figure out, is like, take this Eulerian and Gaussian bit back, figure out how to make it so that that's an envelope and not an asymptote. Carry it on up. This is constant. Talking about the Stefan Boltzmann equation. We recall our previous conversation here where it's discovered that the Boltzmann constant was actually part of this molar gas constant, which is actually a mathematical constant that actually kind of falls out of the golden ratio. What, really? It's like, well, yeah, but by just looking around a little bit at some very simple algebraic formulas, I was able to strike an entire constant in physics into a different one. at least once. You know? The Planck equation can be written in an alternative form. And I wanted to mention Planck because Planck and Angstroms. Oh, great. Here's got Angstroms. Because Planck is 5 orders of magnitude smaller and angstroms are 5 magnitudes greater than the atom. With the wavelength expressed in angstroms. So the wavelength, this is Wien's displacement law. So the wavelength, where was it present? Where does it arrive in this Planck's derivation? I've read through it before, and it sits in with, that's since V equals C over this wavelength. So if C over that wavelength is Planck's angstroms, then and velocity V, that's when you got V cubed over C squared is like so. That's what I'll be looking at to help explain Planck and angstroms. Because in the operationalist and instrumentalist perspective, these are the tweezers where we're trying to catch electrons blindfolded and all this kind of stuff. Rayleigh-Jean's law. This result is commonly used in the derivation of brightness temperatures from radiation measurements at long wavelength, e.g. in the radio frequency portion of the spectrum. It will be noted that under these conditions, the brightness temperature is directly proportional to the rate of energy emission at a given wavelength, or small range about the given wavelength. Particle wave. Hey, have a great day. Good luck. Moment in motion.